Concavity and second derivative test. Concavity. Let f be differentiable at each x in an open interval I. The graph of f is concave up on I if f prime, that is the slope of the graph, is increasing on I. The graph of f is concave down on I if f prime is decreasing on I. Let's look at a couple of pictures that illustrate these definitions. Here the slope is increasing. Near the left end of the graph there's a large negative slope which becomes smaller as we move to the right, eventually becoming positive. Increasing slope results in a graph that is concave up or convex. Here the slope is decreasing. Near the left end of the graph there's a large positive slope which becomes smaller as we move to the right, eventually becoming negative. Decreasing slope results in a graph that is concave down or simply concave. Even though both of these pictures indicate a local extreme value, we point out that that need not be the case. Here's a graph that is concave up where the function is always decreasing. Here's a graph that is concave up where the function is always increasing. This graph is concave down and the function is always increasing. And this graph is concave down while the function is always decreasing. A slopeless interpretation of concavity. Let I be an open interval in the domain of f. If the graph of f is concave up on I, then f of x is less than f of x plus h plus f of x minus h over 2 whenever x plus and minus h are in I. If the graph is concave down on I, then f of x is greater than f of x plus f of x minus h over 2 whenever x plus and minus h are in I. This basically says that if the graph is concave up, given a closed subinterval of I, the value of f at the midpoint is always less than the average of the endpoint values of f. And when the graph is concave down, the value of f at the midpoint is always greater than the average of the endpoint values. This has a simple geometric interpretation. In the concave up case, it says that the point x, f of x on the graph of f always lies below the point x, y that lies on the segment joining x, f of x minus h and x, f of x plus h. Such a segment is called a chord. So roughly speaking, the graph is concave up wherever it lies underneath every chord. Here's another picture that illustrates the idea. Likewise, when the graph of f is concave down, it lies above every chord. Now, to see why the first part of this is true, suppose that f prime is increasing on I. That is, the graph of f is concave up on I. And let x plus and minus h be in I where h is positive. We will show that f of x plus h minus 2 times f of x plus f of x minus h is greater than 0, which is equivalent to the desired inequality. Now let's divide the left side of that inequality by a positive h, and split the fraction into 2, and notice that each has the form of a difference quotient of f. So by the mean value theorem, each of these is equal to some value of f prime. So we have f prime of t minus f prime of s for some number s between x minus h and x, and some number t between x and x plus h. This difference is positive because f prime is increasing. Therefore, f of x plus h minus 2 times f of x plus f of x minus h is greater than 0. The analogous statement about downward concavity may be proved by simply reversing inequalities. Concavity in the second derivative. Let I be an open interval in the domain of f, and suppose that f double prime of x exists for all x in that interval. Then, if the graph of f is concave up on I, then f double prime of x is greater than or equal to 0 for all x in I. If f double prime of x is greater than 0 for all x in I, then the graph of f must be concave up on I. If the graph of f is concave down on I, then f double prime of x is less than or equal to 0 for all x in I, and if f double prime of x is less than 0 for all x in I, then the graph of f is concave down on I. For example, consider f of x equals x squared. F prime of x is 2x, and f double prime of x is equal to 2. Since that's positive, we're guaranteed that the graph of f is concave up on any interval. Now consider f of x equals cosine x. F prime of x is minus sine x, and f double prime of x is minus cosine x. Now notice that f double prime of x is just the negative of f of x. So wherever the function is positive, the second derivative is negative, and the graph is concave down. And wherever the function is negative, the second derivative is positive, and the graph is concave up. Now let's look at f of x equals x to the fourth. F prime of x is 4x cubed, and f double prime of x is 12x squared. Now notice that the graph is indeed concave up, but f double prime of 0 is equal to 0. This is why we can only conclude that f double prime of x is greater than or equal to 0 when the graph of f is concave up. Now let's look at f of x equals x to the 8/5 power. The first derivative is 8/5 times x to the 3/5, and the second derivative is 24 over 25 times x to the minus 2/5 power. The graph of f is always concave up because f prime of x is always increasing. Yet f double prime of 0 does not exist. Example, let f of x equal 2 times x to the 6th minus 9x to the 5th plus 10x to the 4th. Find the intervals on which the graph of f is concave up and the intervals on which the graph of f is concave down. So let's compute derivatives. F prime of x is 12x to the 5th minus 45x to the 4th plus 40x cubed. So the second derivative is 60x to the 4th minus 180 times x cubed plus 120 times x squared. We can factor f double prime of x as follows. It equals 60x squared times x squared minus 3x plus 2, which factors further to give us 60x squared times x minus 1 times x minus 2. So we notice that f double prime of x is equal to 0 at x equals 0, x equals 1, and x equals 2. So f double prime of x is greater than 0 when x is less than 0, because x minus 1 and x minus 2 are both negative when x is less than 0. When x is between 0 and 1, f double prime of x is positive, because x minus 1 and x minus 2 are still both negative. When x is between 1 and 2, f double prime of x is negative, because x minus 1 is positive while x minus 2 is negative. And when x is greater than 2, x minus 1 and x minus 2 are both positive, and so f double prime of x is positive. So we can say that the graph of f is concave up on the open intervals minus infinity to 0, 0 to 1, and 2 to infinity, and the graph of f is concave down on the open interval from 1 to 2. Now let's have a look at the graph of this function. Notice that the graph is concave down between 1 and 2 and concave up everywhere else. In fact, we can combine the two intervals minus infinity to 0 and 0 to 1 and say that the graph of f is concave up on the interval from minus infinity to 1. The 2 points on the graph where the concavity changes from up to down or down to up are called inflection points. In this graph, there are the points 1, 3, and 2, 0. Critical points and local extrema. Recall the following definition and theorem from a preceding lecture. A number C in the interior of the domain of F is called a critical number of F if either f' of C equals 0 or f' of C does not exist. If f of C is a local extreme value, then C is a critical number of F. Now suppose that C is an isolated critical number of F where f' of C equals 0. That is, there's an interval surrounding C that contains no other critical numbers of F. F of C is a local minimum if and only if the graph of F is concave up on an open interval containing C. And f of C is a local maximum if and only if the graph of F is concave down on an open interval containing C. These facts suggest that concavity may be used as a way of classifying critical numbers. In fact, a simplified version of these ideas takes the form of a test called the second derivative test for classifying critical numbers. The second derivative test. Let C be a critical number of F where f' of C equals 0 and f" of C exists. If f" of C is positive, then f of C is a local minimum. If f" of C is less than 0, then f of C is a local maximum. If f" of C equals 0, then f of C may be a local minimum, a local maximum, neither, or even both. That is, the test fails. For example, consider f of x equals x to the fourth. Here f' of 0 is 0, and 0 is the only critical number, and f" of 0 is also 0. And the graph of the function is always concave up, and f of 0 equals 0 is a local minimum. In fact, it's a global minimum. On the other hand, if f of x equals minus x to the fourth, then again f' of 0 equals 0, and 0 is the only critical number, and f" of 0 is also 0. This time, the graph is always concave down, and f of 0 is a local maximum, in fact a global maximum. If f of x equals x cubed, then f' of 0 equals 0, and f" of 0 is also 0, but in this case, f of 0 is neither a local maximum nor a local minimum. Notice that the graph is concave down to the left and concave up to the right, so 0, 0 is an inflection point. For an example where f of C is both a local maximum and a local minimum, we only need to consider any constant function. Example, let f of x equal 3x to the fifth minus 5x cubed. Let's find the critical numbers of f and classify the value of f at each one as a local minimum, local maximum, or neither. Let's compute the first derivative and find the critical numbers. Using the power rule, f' of x is 15x to the fourth minus 15x squared. Factoring gives us 15x squared times x squared minus 1, and further factoring gives us 15x squared times x plus 1 times x minus 1. So we conclude that the critical numbers of f are 0, -1, and plus 1. Now let's compute the second derivative. f" of x, again using the power rule, is 60x cubed minus 30x, and factoring gives us 30x times 2x squared minus 1. Now we'll apply the second derivative test to each of the three critical numbers. Let's start with -1. The value of f" at -1 turns out to be -30, and since that's negative, we conclude that f of -1, which is 2, is a local maximum value. Now let's look at the critical number 1. f" of 1 is 30, and since that's positive, we conclude that f of 1, which is -2, is a local minimum value. Now let's consider 0. The value of f double prime at 0 is 0, so the second derivative test fails. So now let's apply the first derivative test. Since f prime of x does not change sign at x equals 0, this is because of the x squared factor in f prime of x, the first derivative test tells us that f of 0, which is 0, is neither a local minimum nor a local maximum. Example. Let f of x equal x plus 2 times sine x. Find the critical numbers of f in the interval 0 to 2 pi and classify the value of f at each one as a local minimum, local maximum, or neither. Let's start by computing the derivative and finding the critical numbers. F prime of x is 1 plus 2 times cosine x, and that's equal to 0 when cosine x has a value of minus 1/2. So let's think about the unit circle and what angles between 0 and 2 pi give a cosine value of minus 1/2. Those angles are our critical numbers, and they are 2/3 pi and 4/3 pi. Now let's compute the second derivative and apply the second derivative test to each of those critical points. We take the derivative of f prime of x to obtain f double prime of x equal to minus 2 times sine x. Now let's evaluate f double prime at each of the critical points. F double prime at 2/3 pi is equal to minus 2 times the sine of 2/3 pi, which is root 3 over 2. So f double prime of 2/3 pi is negative root 3, which is negative, and so we conclude that the value of f at 2/3 pi, which is 2/3 pi plus 2 times the sine of 2/3 pi, or root 3, is a local maximum value. F double prime at the other critical number, 4/3 pi, is minus 2 times the sine of 4/3 pi, which is negative root 3 over 2. So f double prime at 4/3 pi is equal to positive root 3, and therefore we conclude that the value of f at 4/3 pi, which is 4/3 pi plus 2 times the sine of 4/3 pi, or negative root 3, is a local minimum value. Another example. Let f of x equal x plus 1 over x. Let's find the critical numbers of f and classify the value of f at each one as a local minimum, local maximum, or neither. Let's compute the first derivative and find the critical numbers. F prime of x equals 1 plus the derivative of x to the minus 1 power, which is minus x to the minus 2 power. So f prime of x equals 1 minus 1 over x squared, or x squared minus 1 over x squared. Therefore, we conclude that the critical numbers are plus and minus 1. Let's note that even though f prime of 0 is undefined, it's not a critical number because it's not in the domain of f. So now let's apply the second derivative test to each of the critical numbers, minus 1 and 1. We first compute f double prime of x, which is 2 times x to the minus 3 power, or 2 divided by x cubed. And evaluating f double prime at minus 1 gives us negative 2. Therefore, we conclude that the value of f at minus 1, which is negative 3/2, is a local maximum. The value of f double prime at 1 is positive 2, and therefore the value of f at 1, which is positive 3/2, is a local minimum value.